Gas law number 3 that we're going to deal with is one that's called Gay-Lussac's law. Now, the thing about Gay-Lussac's law is a little back history. Gay-Lussac was a Frenchman, and you have to remember that for a very long time, the scientific community was controlled 100% by the English. And as we know, the French and the English in history really didn't get along with each other. So Gay-Lussac, despite his experiments and despite his analysis of gas laws, he was actually left out of the books, and his law was listed as the pressure-temperature law, because Gay-Lussac's law states that pressure and temperature are directly proportional. So what you would see it in textbooks, even up to when I first started teaching in 2001, 2002, 2003, it just said the pressure-temperature law. And now if you look in your textbook, which is a 2005 book, you'll see that it says Gay-Lussac's law. So it's interesting how history plays into how our textbooks are being created. Now, we're talking about 200 plus years ago that this problem occurred between the British and the French and still played out into the 2000s. So let's talk about pressure and temperature. Pressure and temperature are directly proportional. Again, proportional means changing by the same amount. Directly means in the same direction. So pressure and temperature change equally and in the same direction. So as P goes up, T goes up by the exact same amount. Okay. Again, anytime you deal with temperature in gases, it must be written in kelvins. And here is our law. So P1 over P2 equals T1 over T2. Looks very similar to Charles' law, but instead of volume, now we're dealing with pressures. Again, let's do some examples. Argon is sealed in a metal canister at a pressure of 1 atmosphere and a temperature of 20 degrees Celsius. Over the next hour, the temperature is raised to 50 degrees Celsius. What will be the resulting pressure after this time? So, we start the same way. The first thing you need to do, write down your formula. P1 over P2 equals T1 over T2. Write down what you know. P1 is 1.0 atmospheres. T1 is 20 degrees Celsius, but again, in kelvins. P2 is what I'm solving for because it says what will be the resulting pressure be. And T2 says the temperature has been raised to 50 degrees Celsius, which means that it is now 323 kelvins. Plug it into our formula. 1.0 over P2 is equal to 293 over 323. Go to my handy dandy calculator, and I go 1.0 times 323 divided by 293. Typed something in wrong. Oops. Divided by 293 equals 1.10. Again, it's got two significant figures in the pressure, three significant figures in the temperature, so I have to go by the pressure. So my answer would be 1.1 ATMs. Let's do another. Again, pause the video so that you can do the problem on your own. You'll see that these are getting simpler and simpler as we do more of them. Again, practice makes perfect, makes things so much easier. So, write down your formula, T1. Again, worth a point. Now, I won't take off points if you forget to write the formula and get the problem right. But if you get the problem wrong, I'm taking off a point for the formula, as well as losing points for getting the problem wrong. So, we keep solving. This one, the temperature dropped to 5 degrees Celsius. Means it's now 278 Kelvin. Of course, I look at this and I say, well, if pressure and volume are directly proportional to each other, and my volume has decreased, that basically is going to tell me that, you guessed it, that my pressure had better decreased. Again, my little warning light should go off if I don't get that. So I've got a drop in temperature. I had better have a drop in pressure when I do this. Let's clear up my other calculation. So I've got 278 times 1.0 divided by 293 is 0.948. Excuse me. 0.948 atmospheres. But I only need two significant figures, so this would be 0.95 ATMs. And that's Gay-Lussac's law.